Before we move further with thermodynamics, in particular a study of how heat and work interplay in a heat engine, we need to make something very clear that's profoundly helpful when we try to solve problems, and that involves the concept of a state variable. A state variable is a variable that defines quantitatively the specific state of a system. And important examples include temperature, pressure, volume, mass, and the number of moles present in that mixture that we're studying. Now, if the temperature is a state variable, we know that we can write the internal energy as the number of molecules, 3/2 Boltzmann constant times the temperature. Well, N is constant. Of course, the Boltzmann constant is a constant. And if the temperature is a state variable, then it means that the internal energy, the thermal energy of the system, is also a state variable. But here's the key point. A state variable is independent of the path taken to achieve that state. And we can think in particular about temperature. We know that the internal thermal energy is equal to the number of molecules, 3/2 Boltzmann constant times the temperature. And that temperature, which I can plot on the vertical axis against time during the evolution of what this system experiences, it can go through huge gyrations in temperature, but when it comes to the final point, those molecules can't remember what happened to them. They can only remember what their average temperature is of the ensemble of those molecules. So temperature is independent of the path by which it was achieved. That is, it doesn't matter by what variable or variation temperature went through. If I can define that temperature, that defines the state of the system at that moment. Now let's contrast that with mechanical energy. We know that if I have a mass m and I have elevated it at some height above my 0 point, I know that the potential energy of that mass is equal to mgh. Now, in order to get that mass to that height in the most efficient way, I have to use a frictionless pulley or some other technique that allows me to elevate that mass to some height. However, I could also take that same mass and I could drag it up a pathway by connecting a rope to it and pulling it up that pathway until I reach the same height. But the work that I had to do was much, much greater than mgh, much greater than the potential energy. So while potential energy represents a state variable, work is path dependent. And we have to remember that very carefully when we do thermodynamic calculations. So work is path dependent, but so too is Q. The heat is path dependent. So distinguishing between state variables and variables that are path dependent is a very important part of solving thermodynamic problems. So let's graphically represent how important these state variables are. They are very much like a lighthouse in the storm. They're the fixed points that you can depend on no matter what the other conditions are. And so those state variables are pressure, temperature, volume, the internal thermal energy of the system, the number of moles, the number of molecules that make up the system that we're studying.